Hello! In this video we're going to look at solids of revolution, a type of volume. A solid S is constructed by revolving an area A around a horizontal or vertical axis. In the picture you can see the region A. This region A is rotated around the horizontal x-axis and it sweeps out the solid S. We want to calculate the volume V of the solid of revolution. The first method to calculate the volume V is called the disk method. This is where the solid S is chopped up into a bunch of disks. Then the sum of all those disk volumes will give the volume of the solid S. For a horizontal rotation axis, the volume is the definite integral from A to B of pi r squared with respect to x. And r is the distance from the axis of rotation to the function. A representative rectangle perpendicular to the axis of rotation with small width dx sweeps out a small disk, and each disk has a small volume dv, which is pi r squared dx, where pi r squared is the area of the face of the disk, and dx is the width of the disk. If you are using the disk method with a vertical rotation axis, then your integral will be with respect to y. In the disk method, the representative rectangle is always perpendicular to the axis of rotation. So if you have a vertical rotation axis, then your rectangle is horizontal with small width dy. So the integral must be with respect to y. Again, the representative rectangle will sweep out a small disk, where the volume of each disk is given by dv, which is pi r squared dy. So the definite integral formula gives the sum of all the disk volumes. In this example, we want to find the volume of the solid obtained by rotating around the x-axis, the region under the function x squared, from 0 to 1. So the first thing is to graph the planar region. You can make a small sketch with x squared from 0 to 1, and since we're using the disk method and rotating around the x-axis, the representative rectangle will be perpendicular to the x-axis, and it has width dx. So we're integrating with respect to x. The volume will be the integral from 0 to 1, pi r squared with respect to x, and here r is the height of this rectangle. So on the side I'll just write that r of x is equal to x squared. So we have x squared squared with respect to x. So each slice of the solid is a disk of radius x squared. The radius function x squared is the distance from the rotation axis to the function. So I take the constant pi in the front, and then we just have the integral from 0 to 1 of x to the 4. So the antiderivative of x to the 4 is x to the 5 over 5. Here I can take 1 over 5 in the front. Just check that you get the volume pi over 5 units cubed. And it's not necessary to draw the actual solid of revolution, but here I have put the graph of it just for reference. Next example, find the volume of the solid obtained by rotating the region bounded by x cubed, the lines y is equal to 8 and x is equal to 0, around the y-axis. So again, the first thing, you can draw the planar region. So here you have x cubed, the line y is equal to 8 is on top, and x is equal to 0 is the y-axis. So in this case, we're rotating around the y-axis, so we can draw a representative rectangle perpendicular to the y-axis. So here you can see it has a very small width dy. So our integral will be with respect to y. The integral will be from 0 to 8, pi times the radius squared with respect to y. Since we're integrating with respect to y, we can isolate x from y is equal to x cubed. We can cube root both sides. So x will be equal to y to the power 1/3, or cube root y. So the radius function will be from the axis of rotation to the function. R of y is cube root y. So now it's of the form pi r squared with respect to y, and we can calculate the integral. Since we have a power of a power, we'll multiply the powers. We have y to the 2/3 with respect to y. So y to the 2/3 plus 1 will be y to the 5/3 divided by 5/3, or multiplied by 3 over 5. So we'll take the constant in the front, 3 pi over 5, 8 is to the power 5/3, cube root of 8 is 2, and 2 to the power 5 is 32. So just check if you get 96 pi over 5 units cubed for the volume. And again, you don't have to graph the actual solid of revolution. Here, the graph is given for reference. Sometimes the solid might have a cavity in the middle or it's hollow inside. So then we can use a variation on the disk method called the ring or washer method. So this method is still using disk, you're just subtracting an inner volume from the outer volume. So instead of just pi r squared dx, we have pi times the outer radius squared minus the inner radius squared, and we integrate that with respect to x if we have a horizontal axis of revolution. And if we have a vertical axis of revolution, then we will integrate pi times the outer radius squared minus the inner radius squared with respect to y. In the next example, find the volume of the solid obtained by revolving the region enclosed by y is equal to x and y is equal to x squared about the x-axis. So since the region is enclosed by y is equal to x and y is equal to x squared, we can find the points of intersection. So it will be at 0, 0 and 1, 1. So you can check with the test value in between 0 and 1, like x is equal to half. On that interval, the function x is greater than or equal to x squared. So we know that x is the upper function and x squared is the lower function. And you can make a sketch to confirm that. We're rotating around the x-axis, so the representative rectangles will be perpendicular to the x-axis with small width dx. So the integral will be with respect to x. The outer and inner radius will be from the axis of rotation to the function. So the outer radius, capital R of x, will be just x, and the inner radius, small r of x, will be equal to x squared. So the volume will be pi times the integral from 0 to 1, the outer radius squared minus the inner radius squared with respect to x. X squared squared is x to the 4, antiderivative of x squared is x cubed over 3, minus antiderivative of x to the 4 is x to the 5 over 5. So the volume is pi times 1/3 minus 1/5. So if we put them over common denominator 15, we have 2 pi over 15 units cubed. So again, this graph of the solid is given just for reference. Just note that the inside of this solid is hollow, since the inner volume was subtracted from the outer volume. In the next example, find the volume of the solid obtained by rotating the region from the previous example around the line y is equal to 2. So in the previous example, we rotated around the x-axis, but now we're rotating around another horizontal axis, the line y is equal to 2. So since we're rotating around a horizontal axis, we will still draw the representative rectangle perpendicular to that axis. So it has a small width dx, so our integral will be with respect to x. The outer radius will be from the axis of rotation to the function that's farther away from the axis of rotation, which in the picture we can see is x squared. So when we determine this distance, it's the upper minus the lower. So 2 minus x squared. And the inner radius, small r of x, will be from the axis of rotation to the function that's closer to that axis. And again, it will be upper minus lower. So 2 minus x. So the volume will be given by pi times the definite integral from 0 to 1 of the outer radius squared minus the inner radius squared with respect to x. So we can FOIL out the terms, distribute the minus, and simplify. So the volume is pi times the antiderivative at 1 minus the antiderivative at 0. So just check that you get 8 pi over 15 units cubed. And also this graph is just here for reference, so you can see the solid of revolution. Also note that the inside of this bowl is hollow, since we use the ring or washer method.